Welcome. Let's continue with our discussion of how to speak mathematically. Specifically, let's talk about how to speak the language of relations and functions. So, relations and functions, you understand what a function is. The truth is, a function is a relation. And a relation means I have two sets, A and B. So, this is why we had to do sets first. And a relation then is actually saying that some subset of the Cartesian product of those, where X is related to Y. This is the idea that we have here, that we're going to get an ordered pair, and that ordered pair. Now, this is actually the idea that you already know when you started doing functions, you did X, Y as coordinates in the coordinate plane. And it's kind of important here to understand some key things. Now, we're going to write this, we could write it as an ordered pair like X, Y, but we also, the more common way is we write X, big R, Y. Also, a couple of key pieces of information. We talk about something called a domain. Domain is the set that I'm doing initially, and the codomain is the second set. Now, codomain, you may have sometimes thought about something called range. Range is a subset of the codomain. The codomain, we don't have to use all of it, but it's the entire possible options that could be related, not that are related to something. All right, that's the key thing. So this is our domain and our codomain. And we're going to look at this in terms of what is that. So let's just give an example real quick. Let's look at where the relationship, my domain is set A, which is 1, 2. My codomain is 1, 2, 3. So I've actually already told you the answer to part C. Domain is always the A part, if it's A cross B, or relationship from A to B. So that the from part is the domain. Let me write that in real quick above this. Write that in. Domain. And the codomain is always this. Now, I want you to think for a second, what are all the ordered pairs? Now, realize the relationship, X is related to R, if and only if X is related to Y if X minus Y divided by 2 is an integer. All right, so can you find the ordered pairs in this? Is 1R3 one of those? Is 2R3 one? And is 2R2 one? All right, go ahead and pause the video and just answers questions A and B. All right, so I'm going to assume at this point in time you answer those questions. If you did, then let's look at our answers. Well, all the possible Cartesian products are here: 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and 2, 3. Those are all my possible options. However, as I check them, notice that 1, 1, when I plug it all in, that's 0. However, but 1, 2 is a fraction. It's not an integer. So for that reason, 1, 2 is not in the relationship. And similarly, 1, 3 is in, but 2, 1 is not. And we can continue this by looking at the very next page. And again, we see that 2, 2 is, but 2, 3 is not. So the relationship is actually, notice, a subset of the Cartesian product. It is only a portion of it. So these ordered pairs are the ordered pairs in my relationship. So there's two ways to write a relationship in case you're not picking up on this. One is literally to write the ordered pairs out like this, i.e. set roster notation. The other option is to write it out explicitly with some kind of rule, but this would require us to do essentially set builder notation. So this is why we also, again, did those set notations. Now, coming again, 1, 3 is because, again, 1 minus 3 is -2. Divided by 2 is still -1. So it's an integer, that is. But 2, 3 is not, and 2, 2 is. You can even see, and again, our domain and codomain are here. All right, so I hope you're feeling good with that. Let's try a different one. So when you go ahead and pause the video, this is a relationship that's dealing from R to R, so real numbers, and it's dealing with a circle, i.e. is the point on the circle. Kind of giving the answer to part C. So go ahead and pause the video and answer these questions. All right, coming back. So the first question was, is 1, 0 in here? Is 0, 1 in here? And so forth. Well, because again, I could write it as this form because the relationship is C, so -2, 0, C, or I could write it as this or this. So there's pretty much different ways we can write it. Well, the answer to this first question is 1, 1 is because 1 squared plus 0 squared is 1, but 0 plus 0 squared plus 0 squared is 0, which is not 1, so throw that one out. This one, if I go through the process of squaring them and adding them all together, it works out. Doesn't work. It works. Doesn't work. I know. Every other one, you maybe guessed a pattern, la, la, la. But the idea is that patterns is what we use. And the domain and codomain are both all the real numbers, because remember, that was how we defined it. And the picture is just the circle. Because if we do the XY, if we do the Cartesian plane, we're implying it is all the real numbers. Now, another way that we do this sometimes, we represent this instead of writing X, R, Y, an ordered pair, is we actually draw arrows. So I have, for instance, just to give the idea down here, if X, R, Y, let's say this is my set A, and I literally list them out. So I go X, I could list out a few other things, and over here I list out Y, and this is the set B. So this is my codomain is over on the right-hand side, domain is here. And I draw an arrow going from X to Y. That is how this idea is, and we kind of list them out, and this is kind of gives a visualization of sending them from A to B. This arrow notation, maybe you saw it previously or something else. It does actually use sometimes in algebra. So if I have this one where if A is 1, 2, 3, and B is also 1, 2, 3, I'm going to define S and T in two different ways. So relationship S is if X is less than Y. So if X is less than Y, then X is related to Y. However, in T, I'm explicitly listing out that 2 goes to 1 and 2 goes to 5. If I create the arrow diagrams of this thing, I notice there's a slight problem. My B set should be slightly different. I actually did it as 1, 3, 5. Your textbook did. So it's a little bit off here, but we'll go with it anyways. And notice 1 is less than 3 and 5, so it goes to both of them. 2 is less than 3 and 5, it goes to them, but 3 is only less than 5. Similarly, 2 goes to 1 and 5 because that was exactly what was defined for it. All right, so that is relations. Now, relations on steroids are what are called functions. So relations, here's the interesting part about relations. I'm going to go back a second. Notice in this relation that 1 is related to both 3 and 5. So because 1 is related to two different things, over here, 2 is related to two different things. We don't like that in the situation of functions. So functions are a relation with a domain and codomain. So we're just building on this, but two things. Every element in A has a relationship. That's what it, so everyone has a relationship with something in B. So it has to go somewhere. And secondly, everyone is related to only one thing in B. That's what the second one really says, is when it says that if it's related to two different things, X and Z, then those things have to be equal. So it only is true if essentially every element of X has to go to something and only one thing. All right, so let's kind of understand this a little bit more. We have something like no distinct ordered pairs. Function notation, what we often write is f parentheses x or f of x. You all know this. And in fact, you all write this. So if I'm writing a computer program that has a function in it, it's going to take some input. That's my domain. And if it fails on any of the inputs, that's a massive problem. So it has to work on every possible input. That is what a function must do. That is this idea of property number one, that it has to work for everything I could possibly put in. Number two is that it only has one output possible. If I write a computer program and I can't guarantee what's going to happen, that's a slight problem. I don't want something that's unpredictable. I want something that's very predictable and reliable. I know what I'm getting out. I don't want something unreliable. So to see this, here's an example. So A is 246 and B is 135. If I define the relationship, 2 goes to 5. All right, we draw an arrow. 4 goes to 1, done. 4 goes to 3. That would be similar to this, except it would just add this one extra arrow, and 6 goes to 5. So instead of 6 going to 1, it would go here. Now the question is, if I drew it this way, so ignore this one right here, is this a function? The answer would be no, because notice that 4 goes to 2 values. It goes to both 1 and 3. That breaks property number 2. We don't like that. All right, for the second one, x is related to y if y equals x plus 1. So notice, again, I'm going from A to B. So 2 plus 1 equals 3, which really means that 2, 3 is something. If we go through this list and continue on, 4 goes to 5. And 6, it goes to 7, but there's a problem. Because 7, well, 6 goes to 7 according to this formula here, 7 is not in our codomain. So therefore, it actually violates number 1. All right, now let's look at this actual arrow diagram that we get to look at. Notice that every single one of these has an arrow coming out of it, 2, 4, and 6, and only one arrow going to one location. Therefore, it is a function. So that is yes, I'm sorry, no. The answer to this in terms of is it a function? Again, just to highlight it, would be no, no, and yes. All right. Let me hit one more thing. Let's talk about just a couple more quick things about functions. Let's do an example where we're looking at if A is AB, just 2 letters, and S is a string set of all strings over A. In other words, it's all the possible things. We're going to find a relationship that for every string, Sn means that the length of S is n. So notice here what is the length of this string AB. Well, it has length 6, so this is actually equal to 6, and this one is equal to 3. Because the question is, what is the length of it? Remember, length is how many characters in it, and that is kind of the critical idea. On the other hand, what if I say define a relationship from S to S? So again, S is AB to AB. For all strings, S and T are related, means that T is a string S with just an extra A in it. In other words, I'm adding simply one letter to the left of it. So that is what this is. The questions, so going back, is as we look at this, we found L and A. Here I have this. Now, what we can notice about this particular situation, if we want to observe a little more, is that C of AAB would be A. Sorry, my marker moved on me. A, B, A, B, A, because I would just throw an A, and then the rest of this ends up here. This one would come down, so you still have the B, 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 and all we do is throw an A on the left. So it creates a new kind of situation. It's, again, your book calls this a concatenation. That's a terminology when we combine things and link them together on one side. All right. So one last thing to hit on about functions is what are called function machines. So another way to think about a function is it's a machine. It has an input and it has an output. Put something in and get something out. This makes sense to a lot of things you've done. So the squaring function means I'm going to put something in and I get its value squared. One of the ways to write that symbolically is f sends x to x squared. We could have written this as f of x equals x squared. So all of these kind of have the same idea that we can kind of understand. Another common function is what's called the successor function. And notice it's going from integer to integer. The reason that's important is because it takes any integer and sends me the very next integer. So 2 would go to 3, 3 would go to 4, 4 would go to 5. Negative integers are also allowed. Now, the reason this is highly valuable is actually something we're going to do later on this class. We're actually going to move a successor function for a concept called the principle of mathematical induction. Heads up, that'll come up later in the class. All right, last I want to mention something called a constant function. It's boring. One way to do it is literally from H to Z, meaning you give me any rational number and I give you 2. I mean, I can make that 2, 5. In other words, it always gives out the same output no matter what I put in. It's boring, not cool, but it still illustrates an idea. So all 3 of these are different functions. Now, we can take those functions and we can link them together one after another. We have all sorts of other things we do. Sometimes we just refer to f in terms of f of x, or big G when referring to the function as we've already clarified and explained what it is. Now, again, a relationship is a subset of the Cartesian products, and the function is a special kind of relation. So not all relations are functions. If f and g are both functions, so in other words, they both give some set of ordered pairs, they're equal if when the inputs are the same, the outputs are exactly the same. So to give an example of that, let's consider these 2 functions. So f of x is the absolute value function, and we're dealing with all real numbers from real to real. So real numbers are all my domain. I can put any real number. And the second one is take the square root of the value squared. The question is, are these equal? Well, you can run through a lot of different examples and work through it. Or if you remember from your algebra days, they are indeed equal, because when you take the absolute value of a square, I mean, the square root of a square, it actually gives the absolute value of the value, because the square always returns the positive. So this is indeed true, in part because of the definition about how they work. All right, hope that makes a little more sense about what functions and relations are and gets you started down this path. Again, this week we're just getting ourselves familiar with the language of them. What's a domain? What's a codomain? Because we're going to use a lot of these. We're going to talk about relations and functions and a lot of different kinds of them. Good luck. Let me know what questions you got.